Well, good morning dear. And you have started watching video on principal component analysis. And in that context, actually yesterday, in the earlier lecture, I introduced you with the concept of cars of dimensionality, because the environmental information, let it be image or whatever, speech, we are capturing with the help of some sensors, right? For example, this is captured with the help of some vision sensor. And the way we captured the digital image is actually compatible for further processing in a digital machine, which is computer, right? Maybe our eyes are not visualizing the images like the way computer is visualizing. And there creates a problem, means lots of dimensions are required to represent an image, for example. And we have talked that, okay, even for this image, if I try to input and process for further classification or whatever reason, then the processing becomes extremely difficult if we plan to use fully connected neural network. For example, here the dimension of this W matrix only here in the first layer becomes 1000 cross 3 million. That means there will be 3 billion elements in this matrix itself. So we do not use this kind of fully connected layer. So we use convolutional neural network for processing such data. Philosophically, the idea remains the same. What is that idea? Means we try to represent, we try to learn the representation of the input image. So if the input image dimension is this, then we, after convolution, several convolution, we try to keep as much as possible the information which is there in the input image, but I try to reduce the dimension. Okay. So this is a concept called representation learning. Philosophically, the same thing we would like to do here in principal component as well. And perhaps now you will know that how in an algorithmic way principal component analysis can be formulated, and it can do the representation learning, as I was telling you as a recapitulation, because this is still a 3D object which you can visualize and out of many possible directions on which we can project all the data which are there in my object. Okay, but the direction which actually contains the maximum variance will be the most important direction, because that is capturing the real representation of the data, real representation of the image, right? For example, here I tried to show you that this direction would be the appropriate one rather than this direction. Okay, because if we project all here, okay, the variance, because in higher dimensional feature space I cannot visualize this 3D object, but here you can visualize it. The variance here will be much less than the variance here, and this less variance does not reflect the actual representation of the object. So that's why we try to project in a direction which has maximum variance, okay, of the data. So that's the idea, and now we are ready to formulate the algorithm, which is extremely simple, perhaps the simplest algorithm which you have studied so far, but very elegant one. But before that, I would like to just recap or brush up your statistics basics, which I know you already know. So, the fundamental objective of statistics, as you know, is what? Collect sample from the environment and analyze the sample, okay, and then from this sample try to predict the environment, okay, and when you are collecting sample, the very common way of representing the sample is by its mean, okay, but as you know, the mean does not tell you the true story always, because suppose I have 1, 2, 3, 4, 4 data. This is illustrative data, so it is very small. So what is the mean of this 4 data is 10, and this is another 8, 9, 11, 12. They are complete different sets of data, but they have same mean. So that's why we need another metric to represent the samples in a distinctive way. So that's the idea of, you know, standard. We calculate standard deviation. That means how the data is deviated from the mean, and this is the formula, as you know, the maximum likelihood estimate gives us this formula, and this here is for n number of sample, here is n minus 1, because this is sample standard deviation. Had it been the total population, then you could have figure out standard deviation by dividing it by n, okay. So we have 130 crores of people. So if I collect all the samples, age of all the people, and then standard deviation would be divided by n. But if I collect some sample, then standard deviation of the sample will be n minus 1. That is the idea. So now see the standard deviation for this sample set 1 is, this can be calculated in a very simple way, 0.8, okay, for this is going to be 8.3, and we call it by S, okay, standard deviation, and for sample 2 it is 1.8. Now you see these and these are different, okay. So together with mean and standard deviation is the good representative of a sample set, okay. So this is the concept of standard deviation, which is very, very important metric, as you see now, okay. But then making all on a sudden square of standard deviation, we create another parameter and call it a variance, okay. You know why we do that? Because we would like to accommodate higher dimension of samples, okay. So this is one dimension, you are calculating standard deviation, there is no need of a square. But if you have 2, 3, 4, 5, 6 multiple dimensions, and then standard deviation cannot be standard deviation cannot be calculated. So we introduce, you see, a concept called variance by squaring it, and then you see how we can accommodate. So a square equal to sigma I to n, so square of this term. So xi minus this is the mean square, and then I am writing this square is equals to this term multiplied by this term, and these are 2 dimensions. So I am giving an example of 2 dimension, okay. So in 2 dimension case, the covariance matrix, which basically representing the same or similar idea of variance, that how data is dispersed, but now in 2 directions, x and y, okay. And you can see that covariance between x and y is equals to covariance y and x, obviously, right? So this multiplied by this, or this multiplied by this is the same. So when the dimensionality of the data is 3, for example, then covariance matrix will be the covariance between x and x, x and y, x and z. Then second row, so then actually the covariance has to be in the form of a matrix. Okay, so matrix dimension will be 3 cross 3 because we have 3 dimension. Okay, so and the first row will be covariance between x and x, x and y, x and z, covariance between y and x dimension, covariance y and y. So these are, so diagonals are actually covariance of the standard deviation square, right? So this is you can just see from here. So it's 3 cross 3 matrix. So for n cross n dimensional matrix, this covariance matrix will be written like this. Okay, this is a dimension x is a x dimension of this matrix, and I have written it for your convenience. So basically it is very simple. So you are calculating, first row will be covariance 1 and between 1 and 1, between 1 and 2, covariance between the dimension 1 and 3 up to 1 and n, and then you see the n cross n will be the dimension of the covariance matrix. So you say if n is very large, so you cannot visualize, you can only conceptualize that the deviation of the data from each dimension can be captured with the help of a matrix called covariance matrix, okay, which is a square matrix, always a square matrix. Now, just brush up your concept of eigenvectors and eigenvalue. Let us consider a simple matrix 3, 4, 2, 1. Okay, and I am multiplying it by a vector 1, 2, that is 2 cross 2 matrix, 2 cross 1 matrix. Also, column matrix is called a vector also, So this is matrix multiplication, and I am getting 11, 4, right? 3 plus 8, 11, 2 plus 2, 4. Okay. So 1, 2 is not an eigenvector. But what if I multiply this matrix 3, 4 to 1 by a matrix 2 cross 1 to 1, then 6 plus 4, 10, 2 to 4 plus 1, 5. If you can take 5 common, 2, 1. So 2, 1 is an eigenvector, and 5 is called the eigenvalue. So what is the concept here? If any matrix is multiplied by a vector, okay, and giving back the same vector with which you are multiplying the matrix, then that vector is an eigenvector of this matrix. And you see, if you multiply this with same matrix with this vector, again, you see, 12 plus 8, 20, 8 plus 2, 10. So you see, this will be again 2, 1. So this is, if you multiply the eigenvector with some factor, okay, so again that vector will be again an eigenvector, which you can see from here. So let us try to understand. So not all matrix will have eigenvectors. So you understand what eigenvector means. This matrix has some eigenvector, but this is not one of the eigenvector, but this is one of the eigenvector. And I am not showing here because you have all undergone a course like matrix algebra, and it will be boring for me. But you can just see, recapitulate. If I give you a matrix, square matrix A, how to figure out how to calculate its eigenvector. Okay, so that you can know. This will be very, very fundamental. I am assuming that you know. If not, then come to the discussion forum and we can So you have to do it. So eigenvector can only be found for the square matrix. Please remember, you see, and not every square matrix. Say I have n cross n matrix. Okay, will be guaranteed to have eigenvectors, but if they have, then the number of eigenvectors will be n number of eigenvectors will be there. So here it has an eigenvector, so there will be two eigenvectors. One of them is 2 1, okay, 2 1 4 2, this is 1. Another one, it is your task, you can figure out what is the other eigenvector. I can tell you, but you just, it's very simple example, so you explore yourself what is the other eigenvector. And all the eigenvectors are, this is very important to note for from PCA perspective, that all the eigenvectors are orthogonal to each other. Okay. So with this, now we'll try to understand the PCA algorithm. The basic idea is, I have dimensions, large dimensions, right? And I am trying to reduce logically some dimension, and in doing so I know that I will lose some information, but I can afford it, because if the dimension is large, the example which I gave you, here you see housing price. The housing price more or less depends on some main feature. All others are subsidiary feature because they incrementally influence the housing price. So if I ignore them for the convenience of my computation, then knowing fully that I will lose some information, okay, still my job can be fulfilled. So that is the basic idea of PCA. When you have a huge dimensional data, first what you need to know is to run principal component analysis algorithm and reduce the dimension of the data. So let us see how it works. Extremely simple. So step 1, you have data, and you know the dimension of the data, and you calculate the mean. Okay, so mean will be a matrix if the dimension is large. For each dimension, this is the computation you need to do. Okay, compute the mean first, and then subtract the mean from the data and from new data. As you know from your machine learning knowledge so far, what is this? This is pre-processing of the data, because that will make essentially the data with zero mean. Okay, if you subtract mean from the data, and PCA will work properly if you subtract mean from each of the data dimensions, right? So this is pre-processing of data. This is nothing to do with PCA algorithm as such. Okay. Next, calculate the covariance matrix. If you have C, you need to calculate, and you have now n cross n. If you have n number of dimension, n could be 100, it could be 1000, etc., etc. So those many dimensions, so that will be the dimension of the covariance matrix. So given the data, you can calculate from each dimension. Okay, so this element will be covariance 1, 1, covariance 1, 2. Okay, so it will be huge computation, but this is very simple, very simple formula, you know, covariance. So this is, you need to calculate. Calculation is very easy once you have the data, and then you need to calculate the covariance. Okay, covariance between different dimensions. The data is with you, so you can calculate it, okay, appropriately. Go ahead, and then this is the first step, and the most important step is to calculate the covariance matrix. That's it. Once you have done this, then calculate the eigenvectors and eigenvalue of the covariance matrix. As you know that I calculated eigenvector and eigenvalue. This is eigenvector. This eigenvalue of this matrix is a very tiny matrix, but you know that there are algorithms. Fortunately, you just have to input this matrix and it will calculate the eigenvalues together with the eigenvector. Okay, output you can get. Okay, so you don't have to worry about getting a covariance matrix. Now, once you have got the covariance matrix, then estimate high valued eigenvectors, and your job is to form a feature vector. Okay, form a feature vector. Okay, so form a set of feature vectors actually. And forming a set of feature vectors. How you arrange all the eigenvalues, say lambda I, in the descending order. Okay, lambda 1 coupled with data 1, this is dimension 1, d3. So all this in the descending order you just arrange. Now select a threshold value. Will come why we need threshold afterwards when we will solve a practical problem of say image recognition for using PCA. It's a very interesting one. So we will give a threshold, and the number of high valued lambda can be chosen so as to satisfy this relation, where S is the number of high valued chosen and this is the total number of eigenvalues. So what is the fundamentals here? I have n number of, say, n cross n covariance matrix, and I have n number of eigenvector. But I will not select n because n is a very high dimension. Instead, I will select p dimension. P is much less than n, and that how many will depend on me. Actually depend on threshold. That is, this many you have selected out of total, so you divide by total, and that will be your threshold. Okay. Actually, now selective vectors I am selecting. Okay, because this is convenient for me. And say I am trying to now find the image of a face. I have calculated all the eigenvectors of say 256 cross 256 face image, and now I have decided that I will only use say 64. This is your P. The moment you decide that, you are ignoring many low, and why it is in order of in the descending order, because the low valued vectors are less important according to our hypothesis. So high valued vector, that is like this. Here the high valued vectors will be in this direction, eigenvector. So I will, because this is more important than this. So that's the idea. And in selecting this, of course, we are losing some information, but this is my design. Even if I lose the information, it doesn't matter. I will select the eigenvectors according to the high eigenvalued, okay, and derive new data set which will be lossy definitely. I will just give an example, and before I conclude and tell you more about the algorithm, discuss more about the algorithm in my next lecture. You see, this is the original image, and say it had say 256 cross 256 dimension, and now it is 64 cross 64. I have selected this. So I have lost a lot of information. As you can see, this is known as eigenphase. Eigenphase. This is, you cannot manipulate eigenphase, but computer can, and we can actually write algorithm which I will discuss with an example in the next class. So today you have seen that how just formulating covariance matrix and making the eigenvalue decomposition of the matrix, I can have all the eigenvectors and all the together with eigenvalues which are representing my data. And then you have selected some few out of many, and then you have reconstituted the data which called eigenphase if it is phase data. Okay, so eigen image, okay, rather I should say. So the idea is, although you may lose some information, but even with low dimensional images, we can do some fantastic job which will be suitable for our resources which we have, and I will discuss it in our next class. Till then, enjoy with the simplest principal component analysis algorithm. Come to the discussion forum if you want to know more about it, and stay safe. Have a nice day. Bye bye.